Hello, my name is Rob Reynolds. Welcome to Chapter 3, Section 8. Today we're going to learn about differentials and then look at some word problems, marginal analysis. And there's two basic equations that you need to know for this. One of them you already kind of know. We already know that y prime is sometimes denoted as this. Well, sometimes we write it as dy dx, which stands for the derivative of y with respect to x. So you can see just from this equation right here, if you multiply both sides by dx and dx, we get this equation. And then I'm going to talk to you about part B from a graph in just a minute, but you do need to memorize those two for the test, those two equations. Excuse me. So our objectives is to find differential functions. You'll need these two equations to do that. We're going to use differentials in economics. The change, remember, is the slope. You should, whenever you see change, I want you to think about the derivative. And then we're going to find differential functions using differential formulas, which I'm giving to you here, and there's some others that we're going to learn as well. So remember, the derivative usually is this ratio, change in y over change in x, or slope. And usually we write the derivative as dy dx, remember the lesson as the limit as it approaches 0. So we want this delta change in x to be 0 or approaching 0. So dy dx can be assigned a meaning. As long as dy dx, you can't divide by 0, but we're going to let dy dx be really, really small. So the derivative, dx is equal to the derivative of y with respect to x. But you're going to see in a graph here, we're going to let dx be very, very, very small. So again, I'm trying to make a distinction between a differential and a derivative. And so I'll go through that as well. We'll see the difference between a derivative and a differential. And a differential is just the dx, the differential of x is dx, and the differential of y is dy. Dy dx, of course, and there's that definition that I told you that there it is, that we need again. So dx is the change. This is called delta x. The change. And so what I mean by the change in x, if you look at this graph here, here's the change of x. Good gravy. There's the change of x. It's this distance. So if x is 5 and this is 7, delta x would be 2. So it's just that distance here. So usually what we're going to do is let delta x be really, really small. And so you can see as if I let that distance be really small between the 2 points, the smaller and smaller, then it's approaching, the delta x is approaching 0, and then we get the tangent line. So notice though, if delta x is 2, then this point, that's the, so this would be 5 comma f at 5, and then this would be, well, some distance over. So that's why they're saying start at 5 and then add that delta x to get to f at 7, or the y value. So notice this definition is y minus y. But we're going to just put this in general forms, f of x plus delta x minus f of x. That's part of your difference quotients, if you remember that. We did that earlier, right? F of x plus h minus f of x all over h as the limit as h goes to 0. Well, h is that delta x, change in x that we're letting. So you've seen these formulas before. So again, we're going to let delta x get really, really small, and then when we do that, we're going to find out that dy, which is the differential, is going to be really close to the change in y. And so there it is. Dy is really approximately the change in y. So let me give you an example of what I'm talking about so you can see these approximations. The first thing we want to do is find the derivative. I'm going to change, the first thing I'm going to do is change the color because I'm tired of writing in red. So here's the function, and the derivative of that, of course, would be 2x. Easy enough. So the next thing I'm going to do is try to use this definition and see if we can't find these two things. And let's see, reading up in the problem, they tell me a couple things. You're going to let x be 1. That's not what I want to try. You're going to let x be 1 and delta x be 0.00 or no, just 0.01. So let's do that. F prime 1, and then delta x is 0.01 or 0.01. So finding dy, this says go to the f function, which is right up here, and so this is going to be 2 times 1 times 0.01, which turns out to be 0.02. So I found my dy. The next thing I want to do is find delta y. So again, these are the two definitions that you need. So let's go plug this in. This is f of 1 plus 0.01, which you could just say f of 1.01 minus f at 1. Well, f at 1, if I plug in a 1, really I should be plugging, so f at x is really x squared. It didn't matter, it's the derivative, but you should go back to the original function because it will matter in some cases. But either way, whether you go to the derivative in this case or the original function, but you should go to the original function, f at 1 is 1. And then so this 1 point, you have to evaluate this. So 1.01 squared is 1.0201. And then when you subtract, you get 0.0201. And the goal is to compare these two values. And you can see they're similar. So this is the symbol that we use for approximation. It's approximately the same. They're not exact, but it's a good approximation. Here's the author's worked out solution of that. And that's our first example. So you can see, again, a good approximation. You're welcome to pause the video and rewind the video, but I would go to Blackboard and print off the worksheet so you can see and work along with the video here. So again, here's a visualization of the two graphs that we just looked at. So marginal analysis starts looking at the revenue, and again, it's an approximation of delta R, which again, we've got a nice definition of that, is close to the derivative of R, and you can see these dx's just cancel, but we'll keep that definition running just like we did before. So this is just a story problem. It's the exact same thing that we're doing before in example number 1, but we're going to just have it in terms of economics. So use differentials dr to approximate the change in revenue, and then we're going to compare that. So here's the example, the demand function. Now remember, small p was price, so our revenue is x times p. So our revenue is really x times our price, 400 minus x. So a good revenue equation is 400x minus x squared. Let's see if that's true. Oh, it looks like I step by step worked that out. So I'll just delete this. Well, delete that. Good gravy. There it is. So that's step A. So let's go find dr dx. So dr dx is the derivative of the revenue with respect to x. So the derivative of this thing would just be 400 minus 2x. So remember, the change in R is really approximately dr, because you could go dr dx times dx and cancels out, and you just get dr equals delta R. So let's start plugging things in. We know dr dx, which is this guy right here, is the 400 minus 2x. And we know dx is the change in x, or delta x. And so dx is 1. And let's see, we know x starts at 149. So I'm going to plug in 400 minus 149. No, excuse me. 400 minus 2 times 149 times 1. And I have a nice dr value. And I think this turns out to be 102. So dr is 102. So now we're going to go find delta R. and hopefully we get something similar. So go to the function, and remember the function is right over here. F of x, our revenue function, is 400x minus x squared. So go to the function and plug in x, and remember x is 149. So I'll get 400 times, now this says x plus delta x, and delta x is 1. So instead of saying 149 plus 1, I'll just say 150 minus the function. So wait a minute, I've got to plug into this. So this goes, this says go to the f function, 400x, and in this case, I don't use x. So this is, I'm using the 150. So 400, oh, there it is, 400 times 150 minus 150 squared. Oh my goodness. Let me see if I can just move this over. And of course, it doesn't move over. Okay, let me try this again, because there's two things going on here. Good gravy. So for this guy, I have the function twice. And for this guy, I'm going to use x plus delta x. And x is 149 plus 1. So it's really f at 150 minus f at 149. So I have to do this function twice, and that's why I need a little bit more room. So this guy gives me 400 times 150 minus 150 squared minus then this guy. Ooh, great. And this guy in yellow is minus, and you better remember to put everything in parentheses, 400 times 149 minus 149 squared. Whew! Punch that out, and I think we get close to 101. And then we're comparing that 102 to the 101, and again, we can say it's an approximation. Here's the author. He might have explained it a little bit better than I did, but look, he got the same thing, 102 and 101. But so here's that first function in blue. There's f of x plus h in here in blue, and then here's this in pink. Let's try this one more time, but instead of talking revenue, let's just do it with profit. So this time we have change in profit is approximately dp, and that's because this dp dx times the dx would just cancel. So again, we're going to use delta p to be that f of x plus delta x minus f of x. I'll see if I can do that a little bit better, but we've got to define that function pretty good. So here we go, a new problem, and we're going to try to define who delta p is. And I've got a couple things going on here. Looks like I'm moving from 50 to 150. So if delta p is approximately the derivative of p, then we've already discussed I can use this definition. So, and I can use this definition. So all I'm going to do is plug these two things in. So the first thing we probably want to do, here we go. Here's given p, and then so I'll go find dp dx. That's just the derivative of this thing with respect to x. So it says the derivative of the profit with respect to x. So let's go find dp dx because I need dp dx right here. So dp dx is this guy. So let's go find that first by taking the derivative of this thing. So it turns out to be 0.0006x squared plus 10. And so I'm going to plug that in right here. 0.0006x squared plus 10. And then remember you have that delta x. And delta x isn't always 1, but in this case it is again because I'm going from 50 to 51. And so that tells me delta x is 1. It doesn't have to be 1. I'll show you an example of that in a moment. But if delta x really is a 1, that's just going to cancel out. And I'll have dp. But let's plug in our x value of 50. So x is starting at 50. And then this is f of 50 plus 1 when I get over here. So this is f of the 51 units minus the f of the 50 units. We'll see if we can do that in a moment. So let's see if we can go back over here. And over here, remember, x is 50. So let's plug in the x. So 0.0006, 50 squared plus 10, and if you want to say times 1, you can. So I think this turns out to be $11.50. So over here, we are almost done. All I have to do is go back to the function. So remember, p was equal to 0.0002. X is going to be 51 cubed plus 10 times 51 minus this whole thing again, but instead of 51, this time I'm going to plug in the 50. So 0.0002 times 50 cubed minus 10 times 50. And again, we'll crunch that, and hopefully we'll get something very similar. So let's see if I already have this worked out for us. Here's the 1150 that we had before, and I didn't do the number crunching, but it looks like this term is 536.53, and then this term is 525, and when you subtract, you get 1153. And again, you can see that's a good approximation. And here's a visual. So I told you that I was going to show you the difference between a differential and a derivative. So here are some formulas that we already know for derivatives. We know the product rule and the quotient rule and a bunch of examples. But we're going to compare derivatives to differentials on this next slide. So first of all, if we have x squared, the derivative of that is 2x, but the differential would be 2x dx. Why? Well, remember, if y is equal to x squared, then dy dx is equal to 2x, so therefore dy is equal to 2x dx. And so I'm just doing the difference between here's answer A and here's answer B, and answer A is the derivative, but this is the differential, 2x dx. So let's try that again. The derivative here is 3/5, but the differential is 3/5 dx. How did I do that so fast? Well, this is really 3x 5 over 2/5, and the derivative of 2/5 is just 0. Down here, the derivative is 4x minus 3, but the differential is 4x minus 3 in parentheses, of course, because that dx applies to everything. The derivative here, well, if I rewrite this as x to the negative first, becomes negative 1 over x squared, but the differential is negative 1 over x squared dx. So simple concept, but I just want to make sure you understand the difference between the two. And here are, again, worked out solutions. We're going to try you can try number 5 on your own. I think I've worked out solutions for you, but try to find the differential of this, because you have to rewrite this to be 9 minus x squared to the 1/2, and then do the chain rule, the derivative of the outside, or write down the inside. Don't forget to do x minus 1 times the derivative of the inside. Do you remember that? And then you try to clean this up. So if they ask for the differential, then you don't write y prime, you write dy equals all the stuff cleaned up dx. So here is all that stuff cleaned up dx. So try to get that. If you can't get it, shoot me an email. Here's number 9. Again, you can look at the worked out solutions on Blackboard, but there's one more thing I kind of want to share with you. There's number 9 worked out. 13, oh my goodness, going fast. These are just problems from the book. I want to get to 18 because 18 looks like a problem. Here it is. this is on the test. I'll just tell you, this problem is on the test. This chart is on the test. And we've already defined that dy is equal to -1 over x squared dx. So for the first part, in fact, for the whole chart, we're going to let x be 2. But my dx changes. First we let it be 1, then we let it be a half. So let's see. And then we let it be 0.1. It's getting smaller and smaller and smaller, approaching 0. So if we let x be 1, no, x be 2, so -1 over 2 squared, and then dx is a 1, we get -1 over 4 times 1, which is -1/4. I could write that as -0.25. The next thing it asks for is delta y, and remember we have a nice little definition for delta y. Delta y, it was defined as f of x plus delta x minus f of x. So again, for this whole chart, we're going to let x be 2. So f of 2 plus, it says let delta 1 or delta x be 1 minus f at 2, which really just says f at 3 minus f at 2. And remember, the function was right here. So this is, go to the function, plug in 3, 1/3 minus 1/2, and that turns out to be -0.16, I'll round to 7. Then I'll literally take that number that I just found and subtract off dy and just state the difference, 0.083. And then for the last column, I take this number again and divide by this instead of the difference. It's the quotient. And that's very close to 1.5. And then I repeat this process for delta to be 0.5. So instead of a 1 here, I would do 2 plus 0.5. And then fill in the chart. So you continue with this chart, and then you can see we're going to be making some conclusions here. So there's the first answer. Try this. Go to Blackboard, print off this is off of a worksheet, and try this and see if you don't get these answers. And if you don't, you shoot me some email. And so this is the chart that you're going to have to be filling out, and you can see what's the conclusions here. Oh, well, this is looking like it's approaching. If this gets really small, this looks like it's approaching a 1. There's also another problem here for 26. Again, you can practice this at your leisure, but this video is getting a little bit long for now. But again, here's some worked out solutions. And if you have questions on that, you can shoot me an email. I hope you found this video helpful. Lots of examples here. So go through. There's some 31s answers. Go through and see if you work out a couple more problems. Work your homework. Shoot me some questions off the homework, and I'll try to continue helping you. Good luck on your test.